that is always an option, and we can either find a time tomorrow if I still have slots available. I have to check my emails, or next week, of course. Definitely have options. So um, thank you for, again, just such a vibrant photo board. I pulled some of these from last week. Um, I'm not dead. This is just how I look. I like was dying when I saw that. I was like, for a second, I thought they were like giant French fries or something, and I was like, oh, like okay. Anyway, yeah, good stuff. So let's dig into the content. We're gonna finish up our innate immune response, and so that is all grounded in that quick response to disrupt viruses from replicating and spreading. Um, and then we will transition on time permitting to the adaptive. So who knows how many types of interferon molecules we have? Boom. All right. Suzanne is on it. All right. I hope I didn't lose everyone in the mindfulness. But I hope we're all here. And if not, uh, well, it's gonna be interesting. Okay, so as you can see here in this slide, we have 3 types of interferon cytokines. We have type 1, type 2, and type 3. Pretty straightforward. And they all bind to specific interferon receptors that are shown here in this schematic. Okay. Now, the different types of interferons for type 1, there's a range of them that are present in humans, but most of the textbook and most papers honestly focus on interferon alpha and beta. Those are really well characterized and mediate a broad range of reactions and responses to viral infections. There is one type 2 interferon, which is interferon gamma, and that is the only type 2 interferon. So some of them have lots of types, or I guess individual variations, but for type 2, you have just interferon gamma, and then type 3 interferons are the interferon lambdas are relatively understudied as well, and not as well characterized. But just in terms of a broad overview, this is our interferon family of cytokines. And so I know everyone wants to see another fancy schematic, right? With a lot of signaling pathways, but remember, the big picture is really important here. And these pathways are the host cells system for, for generating an appropriate and rapid immune response. And so up here, you can see that through the detection of RNA viruses, DNA viruses, viral glycolipids, all of these can lead to downstream signaling pathways, right? So we've talked about RIG-I, we've talked about cGAS, we've talked about TRIP. All these things lead to the induction of interferon production, all right? And that also occurs in endosomal compartments with the recognition of genetic material, okay? And so these pathways have a lot of different signaling cascades, but at the end of the day, they're designed to recognize viral particles and antigens and induce an interferon beta and or alpha response. So this is like a race, right? So I know we've talked about this sort of concept before, but basically you have interferons being synthesized, right? It's like this race to synthesize interferons before the virus wipes the cell out and spreads too far and kills the host. So this is a battle, and you say ready, set, go, and go is when you have that recognition event by the host cell receptors, okay? You have the host cell receptors recognize it, and they're off to the races, initiating signaling cascades. Now, maybe the virus has proteins to fight back and disrupt things, but the race is still on. And as interferon beta and interferon alpha are produced, they are then released by these cells, okay? So they generate these large quantities of interferon, depending on the cell type, and then this in turn can go initiate additional signaling pathways from neighboring cells, okay? So I think sometimes students can get tripped up because they're like, all right, there's this race to produce interferon. And then what does interferon do? It's just like, we're going to go to another cell and induce another pathway. And then, I mean, if I was the cell being infected, I'd be like, are you serious right now? Like, what are we doing? What are we doing? We're just like initiating signaling pathways. Like, here's another signaling pathway. It's like, how about let's fight the virus? Who wants to fight the virus? Is anyone going to fight the virus? Or we're just going to initiate signaling pathways, right? So that's the kind of vibe that you can get, but you have to remember, zoom out a little bit, the big picture. Once you have induced the interferon signaling pathway, right, and activated that interferon receptor, this pathway leads to interferon stimulated genes. Now, one downside of the textbook is that they don't really talk about the interferon stimulated genes that much. So I went and pulled a figure. Here's the link to the paper, where it shows all the awesome things that are generated by interferons, okay? So interferon stimulated genes, or ISGs, those include a lot of cool antiviral effectors. That includes CH2 25H, IFITM, TRIM, Viperin, Tetherin, SOX, USP18, etc., right? You're thinking, Dr. Adams, you just said a bunch of mumbo jumbo. Like, what does that mean? Well, I'm so glad you asked. Thank you for asking that question. I'm just going to do one example in the interest of time, but antiviral infectors like Tetherin, super cool. Does anyone know what Tetherin does? Does anyone know what Tetherin does? I'll also put it in the chat. Does anyone know what Tetherin does? Also, is anyone here? Tethers, please explain. Oh my gosh. All right, taking who thinks Fatima should lose a participation point? Actually, probably the classes was all gonna give you props. Okay. Well, class, Fatima, you're staying after class for detention. Extra credit. Oh no, now I'm gonna get like so much like, I'm gonna have a very upbeat class the last month here. It's gonna be rough. At least she was polite. Get out of here. All right. All right. Well, I'm just gonna drop some fire. Boom. Okay, there was, I think, one serious answer in all of this. I remember them from the cellular tethers from HIV viruses. Yeah, good. Yes, Tetherin tethers, okay? So it's literally shown here holding on to HIV virions that are trying to escape. And this is an image. And if you want to know more, take PathMICR 141, also known as PathMICR 140 Fun. next semester, because I'll be teaching it and we will talk about this paper. We will talk about this paper. And so tetherin is produced and then it holds HIV. It's like, you're not going anywhere. Tetherin, or sorry, HIV. Now, unfortunately, this doesn't quite work because HIV has VPU, which is another protein that then like blocks tetherin, but at least the cell is trying, all right? At least it's trying. So that's one example of how our innate immune response is able to stop the viral, it's able to stop the virus from spreading. So it's inhibiting viral shedding, which is basically like preventing a viral wedding. I don't know what direction this flow is heading. Oh, okay. Anyway, so basically we have, this is an example of why interferons are here to save the day, even though it takes them some time to get to the business end of their activity. Here is a simplified schematic of the interferon response, okay? So you have interferon alpha beta binding to its receptor, initiating phosphorylation events and dimerization of a STAT1, STAT2 complex, which can then ultimately reach the nucleus and again induce interferon stimulator response elements. And there's an analogous pathway for IL-6. So again, broad strokes here, cytokines are activating cells to fight the virus. All right, like let's go, let's go. That's basically what the innate immune response is saying to the cells. And while we don't have time to cover all the beautiful mechanisms that exist, the interferon response is basically, and I think this is like too real of an analogy for like California because, you know, forest fires, but basically you have this interferon response and all the cells that are part of that interferon response are instructing the infected cells to like die, right? And then these interferon defined cells are antiviral. So they're like hyper ready to fight off the virus. So it's like, you know, getting amped up, right? Just like, all right, like a little caffeine, a little coffee in your system, a little Red Bull, a little energy jolt, a little cappuccino, a little espresso, a little double espresso. Okay, you got the idea, right? So you have this antiviral state. Everyone is on notice in the interferon milieu, right? The interferon space. And then that protects the unaffected tissues, right? You can generate high amounts of interferon, try and stop the spread, okay? Any questions about interferon responses, interferon activation, interferon vacation? Okay. Then we will just keep moving on, keep pushing. Oh my gosh, what is this? This is a neutrophil. This is a neutrophil. This is the coolest white blood cell ever. Look at it in all its glory. This is at the tail end of chapter 3. But basically neutrophils come through and will fight the good fight right away. I want to highlight that this sort of process of migration has a number of different steps, and that once they have migrated to site of infection, they can do an amazing job just releasing antimicrobial compounds and helping stop the spread of infection. This does vary a lot depending on the pathogen. So an approach for bacteria versus a virus are different. The other thing I want to point out is that the book sort of makes it unclear if this is a lymphocyte or not. It's not a lymphocyte, it's a granulocyte. And we'll talk about that more in the next chapter, but I just wanted to really make sure no one thinks neutrophils are lymphocytes, because they're not. And yes, Fatima, you can't just say like respect for neutrophils after that rude comment. So that's tough. Tough for you. Tough for you. You don't need to know this slide. I just wanted to show you that it's very, very complicated, and don't worry about knowing everything because that's impossible. There's always more going on. Speaking of complicated, why gotta make it sound so complicated? Da, da, da. Okay, clearly I need to listen to that song again. I love this quote because it's like the intro, like they start each chapter with quotes, right? So it's like, life is really simple, but we insist on making it complicated. You can apply that to a lot of aspects of life, but it also really applies to adaptive immunity, right? So adaptive immunity, right? They're characterized by a number of things: speed, antigen specificity, memory, and self-control, okay? Whereas the innate immune response is like, go, smash, that's right, make things happen. That's sort of how that approach, I think, works. Now, there are a number of different analogies you can make for like thinking about the immune response to viral infections. If we think about the innate immune response as like foot soldiers, right, and like maybe tanks going in, then the adaptive immune response is more like siege weaponry. Now, important question. It could guarantee you A in the class. Just kidding, it can't do that. But has anyone played Age of Empires? Anyone? It's like so good. It's like the best computer game. Like, sorry, World of Warcraft, sorry, Dota, sorry, like, I don't know, first person shooter things. Like, this game is amazing. And it is the perfect analogy to understanding the adaptive immune response. So let me walk you through it. All right. You have a LAN party. I mean, I fully support those. I will probably not participate, but this thing just awesome. Oh, Windows Pinball is also excellent, but I would choose AoE to like all day, every day. How many hours I sunk into this, I'll never know, but it's in the thousands. So Minesweeper. Okay, next week, everyone's question is gonna be, or the photo board is gonna be like post your favorite computer game image, and we'll see what's up. Has anyone played Jezball? It's so cool. It's amazing. Okay, so how your adaptive immune response works is as follows, right? You have all the heavy cavalry and stuff at the front, but your adaptive immune response takes a while to set up, but then it unleashes these massive amounts of damage to the invading foe. All right, so catapults, technically these are trebuchets. Okay, they're just like, and they just shoot things, right? And then you have like these scorpions that are also shooting things. Okay, and then you have battering rams, right? Also siege weaponry. Great example of a battering ram is in Lord of the Rings. Lord of the Rings for sure. Well, or an approximation of one. The Two Towers. So these siege weapons are coming in. They took a while to get there, but then they're supposed to deliver the final blow to the infection. All right. So This is straight from the book. I thought this was very nice. All right. It's described as a race against the clock. The virus replication rate, yield, and distribution of the host are pitted against the efficiency of detection and clearance by the host. And the massive clonal expansion of antigen-specific T and B cells is often the fatal blow to a viral infection, which is good, or else like viruses would be like wiping us out all the time, not just during a pandemic. All right. And so the T cells, the cytotoxic CD8 T cells are the battering rams. They get up close and personal, and then they just destroy you. Okay. Whereas the B cells, right, they turn into these plasmacytoid cells. They shoot antibodies from a distance, right? They shoot antibodies from a distance, and then you're like dead, okay, if you're the virus. Although you're already dead because you're a virus, but you know what I mean. So that's how the analogy works. You're welcome. It was amazing. I know. All right. So a little more in terms of specifics for how the adaptive immune response works. I love this photo because, like, can you just imagine like a bunch of like researchers just like, all right, I'm gonna put you in a room and then you're gonna try and figure out like what it is, but you're blindfolded. And it's like an elephant, right? That's how, it's a really good analogy for how our immune response works. It's like, all right, I'm gonna like grab onto this small part of this massive thing, and then it's gonna like be like, do I recognize it or not? And so basically, the adaptive immune response is recognizing very small parts of a virus, right? And those specific components are referred to as the antigen, right? Sorry, I'm following the chat. And so basically T cells are really good at recognizing small linear pieces of viral protein, whereas B cells and antibodies are better with the three-dimensional facets of folded proteins, okay? Together, nice. All right, yes, you could say they're addressing the elephant in the room. Quite a tale, if I don't say so myself. But yes, basically they're trying to get a grasp of what they can recognize, right? That's manageable, and then generate a response that is specific to that antigen component, okay? Now, just to remind everyone, this is gonna be like a brief overview of the adaptive immune system. I'm not teaching you the entire adaptive immune system in like a couple classes, okay? Now, when we think about the adaptive response, there are two complementary actions. You have the humoral response, so you have B cells, and they produce antibodies as plasma cells. And then you also have T cells, okay? And those are going to develop into specific mature T cells that will then also help facilitate the response. So I have a question posed, which is which one is more important for antiviral defense? It's not really one or the other. They're both really important. And I think depending on the viral infection, right, that is going to help you reflect on the nature of the response and the different roles. This schematic nicely illustrates this cooperative event because you have the B cells that will recognize specific viral particles and then release antibodies that inactivate them, okay? So remember, those are like the ones that are shooting things, right? Also, they're like Spider-Man. You then also have CD4 and CD8 T cells, right? So two different variants. And the CD4 cells, they're like sort of the helpers. They will encourage and promote the differentiation of CD8 cells into killing machines, cytotoxic killing machines, excuse me, also known as CTLs, also known as cytotoxic T lymphocytes. And they're just like they have like the hand of death. They're just like, nice to meet you. Oh, you died, right? And then also CD4 cells will help promote this B cell differentiation into plasma cells, right? So both of those very important in the process for mounting a successful adaptive immune response. And then this gives us a nice schematic to just reflect on the family of white blood cells that are fighting the immune response, right? So you can sort of see how they're all related. And in a weird way, this reminds me of mutation rates and phylogenies for different organisms, which is MICR 101. But that that similarity is mostly just at the different lineages, okay? Basically, what you have here are different groups. You have innate cells and adaptive, and they all work together to combat the immune or to combat the viral infection. We, again, to emphasize the role of the B cell, they will synthesize specific antigen receptors, okay? And then based on antigen binding, this will initiate a signal transduction cascade that will ultimately generate memory cells as well as effector plasma cells, which are the ones that are releasing those antibodies to inhibit the infection. All right, so that is all we have for today. That's all I have to say. My jokes are out of the way. I hope you all get an A, and we're done. So, oh yeah, Fatima, stay after class so we can talk.